Our today's topic is error detection and correction using having code. In the previous section, we have already discussed about transmission errors detection using several techniques. Whenever a sender sends some data to a receiver through a transmission medium, some error may occur. Due to interference surrounding the transmission medium, the interfering energy always deteriorates or damage the actual data signal into a different form, such that the digital data 1 bit may be converted to a 0 bit, or a 0 bit may be converted to a 1 bit. And this kind of interference is a very general phenomenon in our surroundings where actually transmission occurs. Transmission medium may be wireless or may be oiled. In oiled medium, electrical signal adjacent to the transmission medium or some other kind of energy, magnetic field, may deteriorate the signal that is transmitted by the sender of the communication system. In wireless, this kind of interference much high, we could say multiple times higher than the wired medium. So the rate of occurrence of this kind of error is much higher in case of wireless network. We need to be aware about this kind of problem, and the receiver side has to receive the data signal that is actually transmitted, has to receive the correct data signal. If any transmission error occurs, the receiver will receive some erroneous signal and something wrong will happen in between the applications running between sender and receiver. So generally, we will employ some techniques for error detection as well as error correction in the sender and the receiving end. Some solutions or some techniques we have seen in the previous section, where we see error detection can be done using some simple process. or some advanced technique like checksum. Using these procedures, the receiver can detect that there is an error in the transmission and we should discard the received message. So what is the result after that? The receiver detects that there is an error in transmission, that is, some binary bits that the sender sends is converted to its opposite. 1 becomes 0 or 0 becomes 1. Some of the certain positions it may occur. Using the above mentioned techniques, we can detect those errors in the receiving end. As a result, the receiver will discard the entire data stream or the entire data unit, and the sender has to resend the whole packet, the whole data unit. Today's topic.
Power on. You've plugged in Unit-1. Your device is ready to pair.
Is error detection and correction using Unit-4. In the previous section, we have already discussed about transmission error detection using several techniques. Whenever a sender sends some data to a receiver to a
Adios, amigo. Powering on.
However, resending the entire data unit is not always a good solution. In case of wired network, nowadays number of internet users are very high, and number of internet users in mobile communication network, that uses wireless medium, is increasing predominantly multiply in multiples. Hence, the bandwidth utilization is a factor in this scenario, because bandwidth is limited. In case of wireless network, it is limited. In case of wired network, it is also not enough, because descending data unit make a congestion in the entire internet, and some delay occurs for the other data unit that has to be reached within a certain time threshold, like live video. But if this kind of applications are hampered due to congestion, which is mainly occurred due to retransmission of data, not desirable in today's network, in today's scenario. We need to reduce number of retransmissions while there are some happening of such kind of interference, and errors happen in the transmission. The beats. Another thing that for only a few number of bits when damaged due to interference, we have to resend the entire data unit. That is also reducing the actual utilization of the resource, that is bandwidth. We can send only that small data unit or data bit, but the TCP/IP protocol should works in such a way that we need to resend the entire data unit, and it will consume a lot of bandwidth, and that is has a severe effect over the entire internet. We need to rethink them, and we think that not only error detection is sufficient in the receiver side, error correction is also necessary. If we make some small error correction in the receiver end, the entire data transmission will be much more efficient. Number of bit transmission will be much lesser. For only a small limited number of bit errors, to remove a limited number of bit errors, if we apply some correction techniques, it will reduce a lot of number of such retransmission. Till now, the techniques that we have discussed, simple event parity checking, or parity checking, only tells us about the error detection. Using data flagged within the data unit is also a simple solution that can say us about error detection. Checksum, that is some additional bit if we send with the data unit, can also detect the error. And it is proved that it is the most efficient procedure that is also followed in nowadays in the internet for data communication. But there is no technique in You will check some correction such that it will correct the data bit error. It only detect. That's it. Running code is a technique which can correct data unit up to a certain limited number of debit error in time. Let's see what is running code and how we generate running code. What is the main basic idea behind running code? We need to know before going actual running code error correction technique. The basic idea in Hamming code starts with some conventional term that is called code word. Code word is nothing else a set of binary bits which consists of data bits and some additional redundancy or check bits. These additional redundancy bits or check bits are added with the data bits to check whether the data bit is correct or not, as well as to a certain extent can make a correction also. We will see later like how the correction. These code words can be valid. Some code words are valid, some code words are invalid. Both the set of valid code words and invalid code words are shared in between the sender and the receiver. Set of code words that actually used to interpret all the data symbols are called valid code words. So there will not be any code word that actually does not represent or interpret any data unit. Apart from this valid code word, there are some other code words which is not used by the sender and receiver pair. Those are called invalid code words. A single bit error can must transfer a valid code word into an invalid code word. That is, if there is a single bit change during transmission, the valid code word will become invalid. It will not transfer into another valid code word. It will always be an invalid code word. So whenever the receiver receives any data unit that does not match with any valid code word that it knows, it will treat it as invalid. Some error is there. We decide. Another conventional term is a distance between code words. If Ci and Cj are two code words, the distance between them is the number of bit positions that actually differs. For example, we have taken here two code words. One is 01101, another one is 10100. Both the code words have same size, and we can see there are three positions where the bits are different. So the distance between them is 3. For example, the first bit position is 0, here it is 1. Second one, it is 1, here it is 0. Third one is same, fourth one is same, fifth one, or the last one, for the first code word is 1, the second one 0. So totally 3 bit positions are different for these two code words. And we can say that the distance between these two code words is 3. We can extend this concept, design and code. Error detection. Now the very first thing before correction, detection. Because obviously can detect error. The convention is saying that for a single bit error detection, the distance between any pair of valid code words must be at least 2. Convention is saying that for a single 1 bit error detection, the distance between any pair of valid code words must be at least 2. Suppose C1 and C2 are two valid code words, and the distance between C1 and C2 is 1. As we have given example, the last bit actually differs. Due to single bit error in C2 in the last bit position, C2 becomes C1. If the last bit of C2 anyhow changed during transmission, it will become C1. This is also a valid keyword for code word. So the receiver cannot identify whether is changed or not. So it is still a valid code word, which is C1. So for a single bit error, the distance should not be less than 2. If the distance between them is 2, then a single bit error will change 1 bit position one bit position is changed, another bit is still different from a valid keyword. Okay? It will never be a valid keyword then, because one bit is changed, and then the distance between itself and any valid keyword will be 1. Will be 1. It will never be same with anyone. That's why error detection will be successful. Similarly, if we extend this concept for k number of bit error, we see that the distance must be at least k plus 1. If k equals to 1, now the main thing the error correction using distance. The main fundamental thing is that when the receiver will receive the code words or error has been taken place, will be converted to an invalid code word. And it will be detected. In the bit position, we know where the actual error happened, then we can just invert the bad bit and make the return. And the thing is that when you receive single bit error data in it, that must be converted to one and only one valid keyword. That is, if we change any one of the bit of that invalid code word, any bit, okay, it is converted to more than one multiple valid keyword, then we cannot determine which valid code word actually has been sent. If it is converted to only one valid keyword, then we can say that valid keyword code word is the actual data unit that has been sent by the sender. For example, first we need to say one thing, that for any single bit error correction, the distance must be between two code words. 3. For detection it was 2, for correction it is 3. We have given an example. Suppose we have sent these two code words 100 and 6-bit data unit or code word, another one is 100 They are transmitted by the sender and they are received by the receiver. Where one bit error is there. For the first code word, the last bit is changed. For the second code word, the fifth bit, that is the second last bit, changed. Okay? Here distance equals to 2, because if you see these two code words, we see that the last two bits are different and the distance between them 2. Now this received code word, we can see this table, the table I have shown at the bottom is a set of invalid and valid code words that belongs to the receiver. So the receiver will check each and every invalid code word first. It sees that both these code words are available in the invalid code word, and so we detect the error detection is successful. Now we see one thing, that both the received code one is same. Both the received code one is same. Now if they both are same, suppose we take the first one and we check against all the valid code words. First we check with the first one, that is 100. We see that there is only one bit change here. That is the last bit. So one bit error has happened. We can say that this is the value. But if we check from the bottom, we can also see there is only one bit error. That is not the last bit, but that is the second last bit. So that valid code word may be the answer. So both the answers are correct. If a conflict, similar thing can happen for C2 also. Check with the valid code word. Both the code words are for this invalid code. Then there is a conflict. Distance equals to 2. Not okay for error correction. Successful error correction. Now we take distance equals to 3. At the first bit differs as well as the last two bits differ. So the distance between C1 and C2 3. Now they are transmitted. The last bit is changed for C1, second last bit changed for C2. Both belongs to some invalid code word set. The receiver end, they are invalid, error is detected, detection is successful. Now if we check now C1, what has been received for C1 with the valid code word. From the beginning, from the bottom, if we check, we see that there are two bit positions which actually differ from it. As there is a single bit error, we can conclude that this valid key code word which resides at the last table, not for C1, not C1, maybe the others. If we check against the second last from the bottom, we can see there is only one bit differs with this invalid code. That is the last bit. So this is the actual valid code word for C1. Similarly, this is the actual valid keyword code word, the last one. We can say that the distance must be at least 3 for error correction. The single bit error correction using Hamming code, distance into k bit error correction, we can say that the distance between any two code words, any two valid code words must be greater than equals to 2k plus 1. We have illustrated using both the distances, that is 2k. Very general thinking will say that 2k may be enough, but actually it will not work. We have illustrated this scenario. Let's say we have two code words C1 at the top left. We have drawn C1 and C2. We have illustrated mainly. The color represents the set of bits. Same color means same set of bits between these two code words. C1 and in C1 and C2, both the first part are common. Same set of bits and same number of bits are also same. Then the next k bits between these two code words are different, as well as the next k bits are different. But suppose these two code words have been changed. Another thing you need to remember that suppose we assume here that the first k bit of C1 is same as the last k number of bits of C2. Similarly, first k number of bits for C2 is same as the last k number of bits of C1. Now some error has been made in the during transmission, and these two code words become, as we have drawn here, that is the last 2k number of bits are now same for both the C1 and C2, and k number of bits error here, but now it is shown, or it happens that both the code words become same. Both the code words become same. Hence, recovery from any of these invalid code word to the original code word is difficult, because both the code words have the same meaning to the receiver. Both are invalid, both are same. So they may be converted into any one valid keyword or two valid code words, and hence there is a conflict. You cannot recover. The main problem is the distance equals to 2k. If we increase this distance just by 1 bit, that we have illustrated at the bottom part of line, in this part, both the keywords are shown, and the last k bit are different for these two keywords. Second last k bits are also different, but in between the common part and the second last k bit part, one single bit is there, which is different from this in these two. For the first code word, if it is 0, for the second one it is 1. For the first it is 1, for the second one it is 0. These code words are designed or are generated in such a way that the distance between them is 2k plus 1, because 2k for the last two parts and this one bit, 2k plus 1. Now when they are transmitted, the first code word C1 will become, k bit will be changed. Suppose the last k bit have been changed, and it becomes now like this. Similarly, for C2, the second last k bit will be changed. It will look like this. So both are almost look like same. That is, they are same almost. Only one middle bit is different. Only one middle bit is different. So even k number of bit errors are there, one bit will always differ in between these two code words. That is actually significant. That actually helps us to find the actual valid keyword separately for these two code words. They will never make any conflict, because the first invalid code word for C1 will always generate one and only one valid code word. For the second invalid keyword code word, it will also generate one and only one. So this is the illustration that helps us to understand distance. In the next slide, we will go actual Hamming code channel. In 1950, Adam Hamming has developed this technique for error correction. Hamming code can correct up to 1 bit and detect up to 2 bits. Minimum distance in Hamming code is 3. Number of redundancy bits is represented as R. Number of data bits are N. then the relation must satisfy to detect error and to correct it. That is 2 to the power r greater than equals to n plus r plus 1. For example, if the number of data bit is 7, n equals to 7, r will be, the minimum value of r will be 4 according to the relation, the inequality. Increase r equals to 5, 6, the inequality will satisfy. But the complexity will also increase, so we will take the minimum value of. We will follow some steps to generate running code using the above formula. Using the above formula, we will first generate how many redundancy bits could be used for a certain size of data. Suppose the size of the data unit is 7, and is n equals to 7. So r will be 4. We have shown here 1, 2, 3, 4, 5, 6, 7. So 7 data bits. D is the data bit. This F1 to F8 is the redundancy bit. Here we have shown the position of the redundancy bits. The first redundancy bit, that is F1, has the position. All the redundancy bits will have the position in the power of 2. That is, the first redundancy bit will sit in the position of 2 to the power 0. Second redundancy bit will be in the position of 2 to the power 1. Third one that is F4 here, that is in 2 to the power 2. That's why we have written as F4. 4 means 2 square. F8, that is 2 cube. Okay. So we have also mentioned here the data bit positions. They are also in those positions. Now we need to determine the value of F1 into F4 and F8 when the value of all the data bits are given. The formula is that for F1, as its position is 1, we will say it covers all the positions whose binary representation includes a 1 in the least significant position. The positions are 1, 2, 3 up to 11 in this section. Now if we represent each and every one in the binary format, we will see that 1 equals to 0 plus 1, that is 1 is there, 3 equals to 0 plus 1 plus 2, that is the binary representation is 0, 1, 1. 5 is 0 plus 1 plus 4, binary representation is 110. 7, the binary representation is 111. In each and every one, the last bit position is 1. That's why F1 has covered all of them which have the last bit position as 1. Similarly, F2 covers all the bit positions whose binary representation include a 1 in the second position on the right. That is 1 in the second position. We represent these positions, suppose 2, 3, 6, 7. You see 2 can be represented as 1, 0. 3 is 1, 1. 6 is 1, 1, 0. So the second position from the right is always 1 on each and every one. And we can say that F2 covers all of them. Similarly, F4 covers 4 to 7, 12 to 15, 20 to 23. F8 exists. For our example, if it does not exist, if it does exist, we cover 8 to 15. Okay? If we represent the covering positions of each and every one in a table will be look like this in for that we have taken. Till now, we don't know the database, but this is a general table is common for any data in value. Whatever the data in each value, the table will be the same. For F1, it will be dependent upon 1, 3, 5, 7, 9, 8. For F2, it will be 2, 3, 6, 7, 10, 11, like this. Okay? One important thing is that F2 never depends upon the bit positions of F1. F3, F4 not dependent upon second position, that is the position of F2. F8 not dependent on, on the position of F4, that is the fourth position. Okay? Now this table is important. Now the last step is that if we perform even parity check for each column of the table, that is for F1, the first column, check the even parity for bit position 1, 3, 5, 7, 9, 11. We need to check total number of ones in the corresponding position column. If it is odd, then F1 must be set to 0. Sorry, if it is even, F1 will be 0. If it is odd, F1 will be 1. Similar thing we will do for F2. If before and after. So the value can be obtained after drawing that table. We give an example here. We take a 7-bit number 100 1101 and we follow the steps that we have illustrated before. Here the number of data bits is 7, so R will be 4. So representation of the code word will be like this. This denotes the redundancy bits as per the table given there. And as per the rules, of parity checking for each and every one, 1, 1, 3, 5, 7, 11, we will decide the value of the bit position F1. Similarly for F2, and F. So this is the result that we will get. This way we can generate code. We illustrate here in this example. In this example, now error correction, how we can make a correction that is involved. Suppose the fifth bit of the above data code word change from 0 to 1. What is the fifth bit? We need to see fifth bit 0. Now it is 1. Same bit and the receive this one. Now we will do the same step 3 here, that is the event parity checking. Okay, we will check for F1 first. F1 will be dependent upon 3, 5, 7, 9, 11 bit position, and we count number 1 there, or the new parity value should be 1. I have written here for F2 in the next row, for F4 in the next row, F in the next row. Now if we go in the bottom up manner, that is from F3 to towards F1, we will see the value is 0101. The decimal equivalent of 0101 equals to 4 plus 1, 5. So the fifth position error has happened. So if the fifth position is now 1, to be 0. Anyway, it was 0, then it should be 1. So this way we can make a error correction using having code. Lot of applications are there in technique. Some exercises may be given like this. This is an example exercise on distance. Suppose an error correcting code has the following code. This one, this one. These are valid codes, okay? What is the maximum number of bit errors that can be corrected? If we see very closely in each and every binary and code words, see that the minimum distance between any pair of code words, so we need the minimum, not the maximum. Okay? Minimum is 4. If maximum bit that can be corrected equals to k, then as it is a correction, then then the distance must be greater than equals to 2k plus 1. Just omit the greater than sign. For simplicity, we write d equals to 2k plus 1. Here d equals to 4 and check. We decide it is 4. Then the value of k will be 1.5. If we get in fractional, we will always take the lower bound because 1.5 number of bits we cannot correct as it is less than 2 and correct up to 1. Similarly, in exercise 2, one exercise can be given on main board. These two tables are given for database and check bits. We need to determine x and y. What we will do? We have to draw that table first, and then we need to count number of 1 and 0s, and we need to decide what the value of x and y will be. The main fundamental thing, we need to draw a table. After the code word table we have drawn here, then for suppose for C1 we need to decide for this check bit in the position 1, 3, 5, 7, 9 up to 11. If the number of 1 is odd, then whether it is odd or even we need to check. And we check here first bullet point we have shown here B1, B3, B0 must be the XOR gate. Absorber of these numbers must be. The result is that x is 0. Similarly, if we write for all the equations and y of this way Hamming code happens. Only the thing remember, Hamming code can correct up to 1 bit position and detect up to 2 bit. Sorry. 1 bit position correction, 1 bit position. That's it for today. Thank you all.